Hello, class. Okay, so today we are going to be talking about Venn diagrams and subsets. And we have some vocabulary we need to talk about. The universe of discourse includes all things under discussion at a given time. In set theory, the universe of discourse is called the universal set, which we're going to abbreviate U. So it's really whatever you're looking at. So let's say we're talking about students at WVC. The universal set in this case would be the set of all students at WVC. And so we would label our set U, and U would represent anybody and everybody within this box. So we're going to take all the students at WVC and we're going to throw them in this box. Now they're either going to be inside the circle or outside the circle. And the circle is going to represent set A. And we can say that set A is the set of people who are enrolled in Math 108. So then A prime, you can make a note, we read this as A prime when you have that little apostrophe there. A prime is everybody who is not enrolled in Math 108. So that would be everybody in the blue. Now there's no way to be in 108 and not in 108. So we take all the students at WVC, we break them into two categories. We say set A are Math 108 students. Set A prime are not Math 108 students. And A prime, you can think of that as not A. So anybody who is not A is outside the circle. Now, the complement of a set, A and A prime are complements. But we're going to define this using our new notation. For any set A within the universal set U, the complement of A, written as A prime, is the set of elements of U that are not elements of A. In other words, we can say that A prime is, now we're going to go set builder notation, the set of all x values such that x is an element of the universal set and x is not an element of set A. So in other words, that's anybody that comes to WVC that chooses to not take 108. Crazy people, why would they not want to take 108? This is fantastic. Okay. So I've got subsets and proper subsets. They're very much the same idea with one slight difference. Oops, let me go a little further there. A subset, we say set A is a subset of set B if every element of A is also an element of B. And we can notate that with this symbol. We say A is a subset of B. So every single element of A can also be found in B. And it might even be the case that these two sets are equal, and that's okay. Quick example of what, well, no, we'll have an example in a second. It could be that these two sets are equal. Now, if this was an algebra class, we could say less than or equal to compare two numbers. You can almost think of this line underneath like that. A is a subset of B, or A could be exactly the same as B. That works. A proper subset is when every element of A is also an element of B, but A and B are not equal. So it's a more restrictive case. Okay, so we're saying A is a proper subset of B if A is a subset of B and A is not equal to B. If we're going to use our notation, we could say that A is a proper subset of B, but not necessarily the same thing. Or it can't even be the same thing. Okay, so find all possible subsets of each of these. Well, one subset might be 1, 2, 1, 2, or the empty set. Every single one of these is a subset of this set 1, 2. And actually, instead of the empty set as being empty braces, let's go ahead and use this other notation. For B, find all possible subsets of the set XYZ. Well, a subset of XYZ could be XYZ. Or it could be XY, XZ, YZ. I think that does all of our 2's. Yep. And then we could have just the set X, just the set Y, just the set Z, or we could have the empty set. And yeah, that rounds it out. So I have the same thing. I have groups of 2. These are all the different ways I can have 2 elements in my subset. These are all the ways I can have 1 element in my subset, or I could have the empty set is a subset. Because everything in the empty set is here. Well, nothing's in there. Okay. Find all possible proper subsets. Now we're going to be more restrictive. For the proper subsets, we have to eliminate the case where they're exactly the same. And so it would be 1, 2, and the empty set. Here it would be all of the ones with 2 elements, all of the ones with 1 element in the empty set, but not that. All right, those are all of the proper subsets of each set. Go ahead and flip your page, please. Counting subsets. Ooh, how exciting is this? Let me see. So if we want to count the number of subsets that we have, To count the number of subsets, we can make a tree diagram to help us out with this. So we're just going to go over to the right-hand side of the paper, and we're going to do a quick example. Let's suppose I have the sets 3, 4. And I want to figure out how many subsets there are for the set 3, 4. Let's make it 3, 4, 5, just to keep it interesting here. That is just so much more interesting. Okay, so I look at the set 3, 4, 5, and I want to see how many different subsets there are. Well, in my new subsets, 3 will either be an element of that subset, or 3 will not be an element of that subset. So we're just going to go through one number at a time, and we're going to say, okay, is this a member of the new subset or an element of? Is this not an element of the new subset, yes or no? So let's look at the number 3. 3 will either be in the subset, or 3 will not be in the subset. Well, let's suppose 3 is. Then the next question is, okay, well, what about 4? Is 4 in the subset or not? And 4 might be in the subset, or 4 might not be in the subset. If 3 was not in the subset, then we still have to ask ourselves about 4. So maybe 3 is not in, but 4 is. Or maybe 3 and 4 both aren't, and that's okay too. So then we ask ourselves, okay, well, what about 5? Is 5 in the new subset? And 5 might be, or 5 might not be. 5 might be, 5 might not be. 5 might be, 5 might not be. And, whoops, that's a 5. 5 might be, and 5 might not be. And so if we follow this tree diagram down, if I follow down the yes, 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 what I get is the subset 3, 4, 5. They're all in. If I follow yes, yes, no, what that is, that's the subset 3, yes, 4, yes, 5, no. If I follow this one down, yes, no, yes, that's going to be 3, 5. And yes, no, no, that's going to be just 3. And so what we're doing here is we're really creating every single combination. 4, 5. This one is just 4. No, no, yes. This is going to be just 5. And no, 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 that's going to be our empty set. And so if I look at this, we did one very similar to this on the front, right? All of the subsets of 3, 4, 5. We have the one that's exactly the same, the 3, the 4, the 5. We have 3 groups where there are 2 elements in each, and we have 3 that have only 1 element, and then we have this last one that's the empty set. And so if we count this up, we have 1, 2, 3, 4, 5, 6, 7, 8 subsets. Now, because every time we're branching off into 2, what we can do is create a formula here. If I have 1 element in my subset, then we're going to have 2 options. The subset of 3 is either going to be 3 or empty. Let's say I add another number to my initial set. Now I have 4 options. I add another number to my set. Now I have 8 options. If I added another number to my set, it would go to 16. And every time we put another number in the set, we're doubling the number of possible subsets, or the number of subsets that we have. So in general, we can say that the number of subsets can be represented by 2 to the nth power. Let's go ahead and write that down. so off the screen. There we go. That's better. So the number of subsets with a set of n elements is 2 to the n. Again, that's if I have one element, there's going to be 2 subsets. If I have 2 elements, there's going to be 4. If I have 3, there's going to be 8. If I have 4, there's going to be 16. If I have 5, there's going to be 32. And on and on and on. So I look at this. How many subsets of the set 6, 7, 8, 9? Well, I look at this and I can say, okay, well, there are 4 elements, so n is 4. The number of subsets is going to be 2 to the 4th power, which is 2 times 2 times 2 times 2, which is 16. And so this has 16 subsets. So what if we weren't talking about subsets? What if we're talking about proper subsets? Well, then we have to subtract the one that's exactly the same, right? I have 16 subsets, but if I make them proper subsets, I have to remove the one that was all yeses in my tree diagram. The one that had the 6, had the 7, had the 8, had the 9. So that's actually going to be 16, but I have to subtract the one that's the same, so it's going to be 15 subsets. And let's make a little note here. We're subtracting one of our sets since we're talking about proper subsets. The set can't be equal. We're getting rid of the set that's 6, 7, 8, and 9. We're taking that one off. So that bumps it down by 1. In general, we have the number of subsets and the number of proper subsets. And those can be represented by the formulas 2 to the n and 2 to the n, but we subtract off the one subset that is equivalent. Now, there's a few practice problems on the bottom. What I'd like you to do is go ahead and practice these, and we will go over them in class next time we meet. Have a wonderful day. Thank you.